So, what is it about approving minutes? We have to approve the minutes of.
All right,
Yeah, I don't know.
so before I forget, if there happens to be a snow day this week, then the test will be pushed back until Friday, Monday. Okay? So if there happens to be a snow day, it'll be Friday, Monday. If there's no snow day, the test will still be Thursday, Friday.
Yes, they said that if we have like a snow day, they won't make us go online, right?
Correct. Yeah. Now, I will say that somebody asked Mrs. Zimmerman about her thoughts on snow days, and she said that she wasn't planning on calling a snow day ever unless there was a power outage.
Okay,
True
well.
story.
Fantastic.
So,
Well, we're talking about.
Our schools
I can't get out of my
so the plan for the rest of the week, today we're doing just one more new thing about integration. And then tomorrow I'll answer any questions you have on anything at all. And then the test will be Thursday and Friday. That's the plan.
Someone just needs to unplug the power at her house.
That's a little frustrating to me because she lives like literally like right there.
Yeah.
I don't live right there.
Yeah.
Anyway, so we're going to talk about today integration. Involving inverse trig functions. So remember, we have these rules for derivatives for inverse trig functions. And they are the derivative of inverse sine x. Anybody remember what that is, the rule?
1 over the square root of 1 minus x squared, right?
Very nice. Good. I always forget these. Like I have to look them up just before I talk about them every time because I forget them. And then there was the derivative of cosine inverse, which is just -1 over the square root of 1 minus x squared. Right? And then the derivative of inverse tangent. What's that one?
1 over x squared plus 1.
Yeah, good job. 1 over x squared plus 1. The derivative of cotangent inverse x is -1 over x squared plus 1. And then the last one was the derivative of secant inverse x.
Square root of x squared.
No, it's like absolute value. So
1 over absolute value of x, square root of x squared minus 1. And the derivative of secant inverse x is -1 over the absolute value of x radical x squared minus 1. Okay? There'll be one multiple choice question on one of these formulas on the actual AP test. That's it. That's what you need to know it for. But it's something that, you know, one multiple choice question that could be the difference between a 4 and a 5 or whatever. So it's worth taking a look at just before you walk into the test. All right, so there's obvious integral rules that are just opposites of these. So the integral of 1 over the square root of 1 minus x squared is inverse sine x plus c. The integral of 1 over x squared plus 1 is inverse tangent x plus c. And the integral of 1 over x radical x squared minus 1 is secant inverse x plus c. If there happens to be a negative in front of any of these, you could just have it be negative sine inverse, negative tangent inverse, negative secant inverse. Okay?
So if it was like negative, it would just be cosine?
Yeah, I mean, it could be either. It could be either one. But just, I would just be aware that it could be, yeah, it could be either. I'm trying to think, like, if I was trying to fool someone, what would I have the multiple choice be? Like, just be aware that they're both possibilities. Yeah.
Why don't you want the absolute value on the last one?
Great question. I don't know. I'm trying to think why there's an absolute value in the derivative rule to begin with. I can't remember what the reason for
I
that
feel
is.
like we solved it.
Yeah,
Yeah, we went over it why.
Yeah, this is one of those things that I always forget. I can't remember off the top of my head. Sorry.
Okay.
All right. So more often than not, the question won't look exactly like this, which is why we're spending a day on it today. Sometimes it'll involve u substitution or some other little process to make it look like those. For example, suppose you have something like the integral of 1 over 1 plus 4x squared. Yeah. So this doesn't look exactly like any of these, but which one does it look most like? Yeah, to me it looks most like the second one, and it turns out that it is some variation of that second one. So what you have to do is you have to kind of make it look like something like this. So in this case, you could write this as the integral of 1 over 1 plus 2x squared, and then use u substitution. So you could say, in this case, u is equal to 2x, and then du is equal to 2 dx. So dx equals du over 2. And then if you make that substitution, this is just the integral of 1 over 1 plus u squared times du over 2, which is just going to be 1/2 inverse tangent u plus c. So the answer is 1/2 inverse tangent of 2x plus c. That would be the answer. I think this is a good opportunity for me to tell you about a little shortcut for u substitution. So this is a really valuable shortcut. So the shortcut is this. If you have to use u substitution, substitution, and the u that you're going to pick has a derivative that's just a constant. The u you'll pick has a derivative that's just a constant. Like in this example that I just gave. Right? In this example that I just gave, the derivative of u was 2, right? So the derivative is just a constant. then don't do u substitution. Just pretend like you don't have to do u substitution, and all you have to do is divide by that constant in the end. Like here, you just pretend like you don't have to do u substitution. This would be inverse tangent of 2x, but then just divide by 2 in the end. That's always how it's going to turn out. Okay, you'll save yourself a lot of time doing that, because that happens quite often. If you have to use u substitution and you'll pick as a derivative, that's just a constant, then don't do u substitution. But just divide by the constant in the end. Let me give you a couple of examples of this shortcut, then we'll go back to the inverse trig. So let me get my notes from yesterday and see if I can find some examples like that. So like, for example, let's say you have something like the integral of the square root of 3 minus 2x dx. This answer, without doing any time-consuming work, the answer is just going to be, this is something to the 1/2. The u that I would pick in this case would be 3 minus 2x, right? Its derivative is a constant, -2. So if this is 3 minus 2x to the 1/2, its integral is just going to be 3 minus 2x to the 3/2 times 2/3, and then just multiply the denominator, like divide by -2. That's the answer. You see how that shortcut works? Like normally, if this was just something like the integral of u to the 1/2, its integral would be u to the 3/2 times 2/3, right? So all you're going to do differently is you're just going to divide this by the derivative of whatever u you were going to pick, if that derivative happens to be a constant. That might seem a little complicated, but it's, once you get used to it, it's super much quicker. It's a super time saver, okay? Let me give you another example. Suppose it was something like, okay, so suppose it was like secant of x plus pi over 2 tangent of x plus pi over 2 dx. The answer would just be like the integral of secant u tangent u is just secant u. So this would just be secant of x plus pi over 2 divided by 1, since the derivative, in this case, I would pick u to be x plus pi over 2 and its derivative is 1. So I divide by 1 just to show you that I'm doing it, but you don't really have to write that, obviously. And that's it. That's the answer. You don't really have to do u substitution, so you're saving all that work. Okay? And find another one. Just in my notes that turns out that way. How about something like the integral of secant squared of 4x plus 5? What do you think the answer would be? Perfect, yeah. Almost. Plus. Does that make sense? Everybody see the shortcut? All right, so let's go back to the inverse trig then. And I'll review this stuff after break too, when we resume talking about unit 4. But this is a really important shortcut that's used really often. I'll use it really often. Okay, let's do another example for inverse trig then. How about something like the integral of sine x over 1 plus cosine squared x? Any ideas? Anything we could do? Let's go back up here. Remember, these are the rules for the inverse trig. Does this look like any of those, kind of? Kind of? Okay, so how could I make this look like the rule for tangent?
Maybe rewrite it as 1 plus cosine squared.
Okay, so it is 1 plus something squared on the bottom, which is good. But then you got that stuff on top. Any idea how we could get rid of that?
Like u sine x.
Yeah, let u be cosine x.
Yeah.
Right, because if you let u be cosine x, this is a constant multiple of its derivative right here. It'll cancel out if we use u substitution. So u is cosine x, du is negative sine x dx, dx is negative du over sine x. So then substitute in. So now I have the integral of sine x over 1 plus u squared times negative du over sine x. So the sine x cancels, which is good. That's what we wanted to have happen. So this is negative inverse tangent of u plus c. Or I could have written inverse cotangent of u plus c, right? It would be the same thing. Now wait, I'm gonna rephrase that. It's not the same thing. How are those two functions related? How is negative inverse tangent related to negative or positive inverse cotangent? Yeah, exactly. They're vertical translations of one another. So either one is an acceptable answer. When you're finding an antiderivative, it's an antiderivative. It's not the only antiderivative. There's infinitely many antiderivatives, right? So we could use this, or we could use inverse cotangent, positive. So this would be negative inverse tangent of cosine x plus c. That's the answer. Okay. Let's try another one. How about this one? The integral of 1 over x radical 3x squared minus 1. Which one does this kind of look like? Inverse secant, right? But there's this troublesome little 3 here, but it's not that hard to fix. This is more like the first one we did. You could write this as 1 over x radical 3x squared minus 1. Yes. Now this one isn't quite the shortcut that I was telling you about, because in the shortcut that I was telling you about, that I was telling you about, yes, you're going to have to use u substitution, and the u you'll pick would be have a derivative that's constant. Is it the shortcut that I was telling you about? Might be the shortcut I was telling you about. Yeah, kind of seems like it will be. I'm a little confused. All right, so here's why I'm a little bit confused, because it's not the same thing here and here, right? I'm not squaring the same thing here that I have out front. So that's a little confusing to me, but let's just do it. Let's do u substitution and let's see if the shortcut applies. That's a good way to solve this. So u would be radical 3x. Du would be radical 3 dx. So dx equals du over radical 3. Yeah, it does seem like it's just going to turn out to be the shortcut. So this is going to be the integral of 1 over, okay, so it's not quite, because then you're going to have this x here that's not going to cancel with anything. Ooh, how do you fix this? Okay, this is a good one. What do you do? Right, everybody see the problem? If I do what I'm going to do, which is 1 over the square root of u squared minus 1 du over radical 3. There's nothing that cancels with that x. So what can I do? Really?
You gotta save the time on the AP test. Let's move on.
Just pick C?
Star it, come back to it later.
Okay, so you have a half hour left at the end because you know everything so well, and you're coming back to it later. Then what do you do?
Would it be helpful at all to get one of the extras on the top? 'Cause then,
Get one of the x's on top. What do you mean?
like, in order for there to
Wait,
even be a
Mr.
possibility of anything canceling, you would need an X on top of one and X on the bottom of the other, which makes,
I agree.
And you, like multiply it out and you get radical 3x times the square root of u squared minus 1. And then wouldn't that just be u times radical u squared minus 1? Because you set u equals
Wait, say that again. Can you what? Multiply it out.
in the green writing.
The green writing. Multiply what out?
Like it would be 1 over radical 3 and you multiply that times 1 over x radical. Basically you would get, on the left there, you would have 1 over radical 3x times radical u squared minus 1. And then 1 over radical 3x is equal to u. Then it would be 1 over u times u squared minus 1.
Oh, that's a really good idea. That's kind of what I was going to do. Yeah, okay. Does everybody see what he's saying? He's saying if you take this radical 3 and this x, that actually equals u if you put them together. That's right here. So this is really the integral of 1 over u times the square root of u squared minus 1 du. I was going to do something similar. What I was going to do is I was going to say, let's replace this x. If u is radical 3x, then x is u divided by radical 3. Just get hot as balls in here all of a sudden?
Yeah.
What the hell? All right, so then you just take this and you just plug it in there. That's what I was thinking. And then the radical 3 here cancels with the radical 3 there.
Especially while I was talking there, man.
I'm gonna pass out. I gotta open the window. It's also hot as ovaries. Just a little opportunity. Yeah, so the answer would be inverse secant x or u plus c. So it's inverse secant of radical 3x plus c. That was a tough one. Does everybody understand what we did? I like your thing better, but my thing works more often in other types of problems, but that's a really good observation. Okay? Let's try another one. Goodness gracious, it's hot. Whew. How about this one? Integral of dx over square root of 4 minus x squared. Crap, look at it. All right, so what do you think? What does this one look like? This one kind of looks like inverse sine. So what's wrong is this is a 4 and not a 1. There, I stated the obvious. Things like overheating, do you hear it?
Yeah.
This is wasteful.
Yeah, so it's just.
There's gotta be something wrong here, right? Am I wrong?
Something's wrong.
Okay.
Our school's freezing, so.
Like,
It's just
I
like.
think I have a fever. All of a sudden. All right. What do we do? There's a 4 here. We don't want that 4 here. What can I do to get that 4 out of there? What if I were to multiply the bottom by 1 over the square root of 4, or the square root of 1/4? And then just do the same thing on top. That's legal, right? I could multiply the top and the bottom by a constant. It's just like multiplying by 1. And then what that does is it fixes the bottom. Like the top, I get 1/2. Like that 1/2 is still there. But now on the bottom, I can take this 1/4 and distribute it. Since it's under a radical, I can multiply the 2 radicals together by distributing. And I would get the square root of 1 minus x squared over 4. Which is really, I can put the 1/2 out front. And I can write the bottom as square root of 1 minus x over 2 squared. Now it's the shortcut. The shortcut is, if I think I'm going to have to use u substitution here, but the u that I'm going to pick has a derivative that's a constant. The u I would pick here would be x over 2. Its derivative is a constant, 1/2. Then I really don't have to use u substitution. I can just divide by that constant. So this is going to be 1/2 from there, sine inverse of x over 2 divided by 1/2. And then the halves cancel. That's the answer. Everybody see that trick? All right. Let's do another one. How about this one? The integral of dx over square root of 9 minus 4x squared. What do you think here? Kind of the same thing, right? What should I multiply the top and bottom by? Yeah, square root of 1/9. Or 1/3, really. Right? So this is just going to be 1/3 integral of dx over, if I distribute that 9 into the radical, I get square root of 1 minus 4/9 x squared, which is 2/3 x squared. So the answer is 1/3 inverse sine of 2/3 x divided by 2/3, which 1/3 divided by 2/3 is 1/2, right? So this would be, yeah, so it would be inverse sine of 2/3 x divided by 2 plus c. That make sense? So these problems require a little bit of thought, but you have to know those 3 basic rules for inverse trig functions. And then just think about which one does this look like and how can I make it look like that even more? Like what's wrong with it? How is it not exactly like what it should be? Like in this case, what makes this not exactly what it should be is the fact that that's a 4 and not a 1. So how can you get rid of that 4? That's the idea. Okay, any questions about that? Okay. I'm gonna slap it.